see. So green light on me, and orange is the circle.
Okay. Okay, you remember what I was doing last time? I didn't talk about Stokes flows, which is our ultimate aim, but I will today in a few minutes. So let me just review what we did last time. Okay, so last time we looked at so incompressible, ideal, ideal meaning that there's no viscosity, and irrotational flow. Is described by a stream function, I called it psi. Such that I can think of psi as the imaginary part of some analytic function. You remember how I defined an analytic function? Simply as one that doesn't depend. If you think of this, if you think of moving from an XY Cartesian system to just the same place, but just a different description in terms of the two conformal, complex variables z and z bar, then an analytic function is one that does not depend on z bar. Okay. So we were able to, that's what we did last time. We saw that the stream function is the imaginary part of the analytic function. And then something else we showed was a point vortex of circulation gamma, say, at Z0 is given by this complex potential. It's a special one. Okay. Where this W hat is doesn't have any singularities at Z0. Okay, that's what we did last time. And in fact, I went a bit further, didn't I? I put one of these. So, point vortex basically has streamlines. Oh, by the way, how do you determine the suppose my complex potential is this, so it's just a point vortex. So in other words, W hat is 0. How do you determine the stream lines? These are actually the stream lines for this flow, but how could I determine these? This is Z0 there. Well, remember, the stream lines are the contours of this stream function. So lines of constant psi are the stream lines. And so let's work out the imaginary part of this thing. And just remember that complex logarithm looks like this. Log mod plus I argument. Okay, that's the complex logarithm there. And of course, the imaginary part is just this thing. Okay? So the imaginary part is just this. And you can see that this is clearly only constant if the modulus of z minus z0 is constant, which are circles centered at z0. Okay. Did I want to say anything? Oh, I didn't tell you. By the way, we also did this, didn't we? We put this vortex near a wall. What else we did? And we noticed, we worked out what the complex potential was. In other words, we worked out what this W hat had to be so that this wall is a streamline. And we actually worked out the dynamics of the point vortex. And we found that if this is at height b above the wall, then in fact it moves with speed u given by gamma over 4 pi b. Everybody remember? I didn't tell you, however, there was something else I started to look at. I didn't tell you the answer, and I'm not, to tell you the answer, I'm not going to go through all the details. Remember, I put a gap in the wall. And then I had this vortex over here. And I never told you what it did. I think we vaguely discussed it. We decided, so suppose this is -1 and 1. I think we discussed if it was sufficiently high, it would perhaps dip a little bit when it was above the gap, but then would basically carry on as usual. And that is in fact true. I can't remember if I told you that what happens is, if it gets sufficiently close to the wall, it will do the following thing. So in other words, if it's very close to the wall, then of course it will travel, just like this does, it will travel with some speed very close to that u. And then what will happen is, as it gets close to the gap, it will actually double back on itself and come around like that. Okay, so if it starts far up here, the trajectory is the following. It will dip a little bit, but carry on. And if it's close enough to the wall, it will actually go around the bend. Okay, and there's actually a critical separatrix between these two behaviors, which is symmetric with respect to the gap. This separatrix. And in fact, if this gap distance is 2, this height is 1. A critical trajectory. So the message is, very interesting result, that if your vortex starts less than half the gap width away from the wall, it will go through the gap. You see, half the gap width is 1. If it starts off closer than 1 from the wall, it will go through. Otherwise, it just skips, goes over. Okay. By the way, I won't go through this, but it was this calculation appeared in a paper by Johnson and McDonald. Takashi knows Rob. And this was in 2004, I think it was, in Physics of Fluids. It's interesting that it was only 10 years ago that this was actually studied. Okay, that was a review. Let's go to what we really care about. Stokes flows in 2D. Okay, so we're still in the xy plane, but we're trying to solve Stokes equations now. So we want to solve these equations. And it's still incompressible. And by the way, so I have set in these equations the fluid viscosity, this is a very important note, to 1. Okay, so sometimes you see a mu or some parameter here. Some people put a mu here to describe the viscosity. But basically, I've set it to be equal to 1 because we can rescale things here. But don't forget, the reason I'm emphasizing this is that I don't want to have viscosities everywhere. But this is an intrinsically viscous flow, whereas all of this was relevant in a completely different regime where the viscosity was infinite. That was zero, I mean, with no viscosity. So now we've got a very viscous flow. But it's incompressible. And it's 2D. So we can still introduce the stream functions. Psi. So such that psi, d psi by dy is u and minus d psi by dx is v. Okay? So that's exactly what we had before to describe inviscid, non-viscous flows. Okay? Let's just look at the vorticity. Which, by the way, you can't really take the curl. Vorticity, by the way, is defined to be the curl of velocity fields. You can't do this really in 2 dimensions, but you can embed it in 3 dimensions. And I think I said this last time, you get just a component in this 3rd direction, which we call omega. Which is this. Okay? U, by the way, is UV, but we're kind of embedding it in UV0. That's what we're really doing here. We don't need to actually do it, we're just thinking of it like that. So this allows us to deduce what this vorticity is in terms of the psi. So it's dv by dx minus du by dy. And now let's substitute from the box. Okay, just substitute from here. So this is minus del squared psi. So that's quite an important thing for us to remember. This is true, by the way, of any 2-dimensional incompressible flow, viscous or not. But let's take a curl of the Stokes equations. Once we've embedded in 3 space again, of course. And the curl of grad P is 0. And the curl of the left-hand side is del squared of curl U, which is the vorticity. So, So what we conclude here is the vorticity is harmonic in Stokes. And let's call that star star. And the stream function is biharmonic, because if we combine that equation with this, we can see that. Everybody see? Any questions? You okay? So, as with ideal flow with no viscosity, which by the way you can think of as infinite Reynolds number, we have a stream function and a complex potential of which its imaginary part Wz if it's irrotational. And then here we have a biharmonic stream function. The stream function there was harmonic, irrotational flow. So notice, look, this was what I had on Tuesday. I'm going to find something similar now for the zero Reynolds number case, where the very viscous fluids. So of course, all I'm going to do is change variables from x, y to z, z bar. You remember this, everybody, I hope. D by dz is 1 over 2 d by dx. What's this? Remember this? Z is x plus iy, so this is minus I d by dy. So we notice that del squared is, of course, this, and we know that this is 4 d squared by dz dz bar. Okay? I did that last time. So clearly, del 4, which is where you compose this with itself, is 16 d4 by dz bar squared dz squared. So, if this stream function, this real stream function, is biharmonic, that's equivalent to this. And you can see what I'm going to do, just like I did before. I can see how I can integrate this. So let's do it piece by piece, just so you can see where this comes from. Let's write it like this. I've just taken one of these out. You can see then that this function is an analytic function. Because remember, the definition of an analytic function is one that doesn't depend upon z bar. Just get my notes so I get the notation consistent. So, and what I'm going to do then is d cubed psi by dz bar dz squared is some analytic function, arbitrary analytic function. I'm going to call it the second z derivative of some arbitrary function p. I'm just calling it second derivative just for convenience. It's an arbitrary function. But you can see I can integrate this again with respect to z bar. So let's do that. What's the integral of this with respect to z bar? It's just a function of z. So as far as z bar is concerned, it's a constant. So it's z bar, p double prime of z, whatever that function is, plus another arbitrary function of z. So let's call that one q prime prime of z. So that's another arbitrary analytic function. You can just check, look. Suppose I took 2z, this is a linear in z bar. So clearly 2 z bar derivatives will give me nothing. P and Q are arbitrary. Everyone okay? And now look, I've just got z derivatives everywhere. So let me integrate, but being careful. So let me integrate once with respect to z. What's the integral of this thing with respect to z? It's conveniently, that's why I did it, it's p prime. This one is q prime. Well, what else do I get? I'm integrating with respect to z, keeping z bar fixed. Of course, at this stage, I could in fact have an arbitrary function of z bar coming in. I think I'm calling that r of z. This is arbitrary function. Arbitrary, remember, I called this an anti-analytic function. But whatever. And I've got one more integration to do. The integral of this with respect to z is z bar p. You can see why I put the double derivative there now. All of these things are arbitrary, plus q of z. What's the integral of this with respect to z? It's z r of z bar. Z bar is fixed, it's constant, plus, of course, s of z bar. Where this is another arbitrary analytic function. But, just like Tuesday, I need this to be real for all z and z bar. So it looks like I've got 2 analytic and 2 anti-analytic functions here. But in fact, R and S have to be related to P and Q. So real for all z and z bar. We must pick the following. R of z is p bar of z, which remember is defined to be p of z bar bar. This is the conjugate to p. And s of z must be q bar z. This is the Schwartz conjugate. In other words, R has to be the Schwartz conjugate of P, S has to be the Schwartz conjugate of Q. Exactly the same as Tuesday. So, in particular, look, R of Z bar, which is what I need here, look, will be P of Z all conjugated. Which means that this and this will be complex conjugates. Want to see? Similarly, this will always be the complex conjugate of this. That will guarantee that psi is always real. So we finished. So the nice thing is we get the general solution. Don't forget, P and Q are arbitrary. So letting f of z be 2i p of z, g of z being 2i q of z, which are equally arbitrary. If p and q are arbitrary, then we get the psi is the imaginary part of z bar f plus g. I just did that to put it in the standard notation. F and G are the things we're going to be dealing with for the rest of the course. The rest of the course is all about how do you find F and G. So these are complex potentials, or as I mentioned on Tuesday, based from the plane elasticity literature, people call these Gauss functions. Everyone happy? So, the only difference now between the whole of the thing I talked about on Tuesday, which is ideal flow, the only difference now, when we're dealing with Stokes flow, is we've got two complex potentials, F and G, in order to determine the stream function. By the way, just if you're out of interest, if you're interested in solid mechanics, everything I say henceforth is true there too, except interpreted differently, and it's slightly, there's some more parameters coming in there, but psi there is known as the Airy stress function, and there's entire monographs by Muskeleshvili from the middle part of last century. A whole several hundred-page monographs that deal with this representation in the context of plane elasticity solid mechanics. Unfortunately, there aren't any textbooks on what I'm going to tell you today and next week. For Stokes flow, this formulation is used much less often. So look what we've got to do now. We've got to, what would be helpful is to get all the physical variables in terms of F and G. That's the stream function in terms of F and G. Let's look at by the way, let's just write it like this. So let's look at U minus IV. Okay, we know the stream function. Let's work out what the velocity is in terms of F and G. Well, remember, here's the velocity fields in terms of psi. So U minus IV, look, is psi by dy plus I d psi by dx. Let's take the I outside. What's this thing? It's got the minus there. So it's d by dz, partial d by dz. 2 times partial dz. So this is 2I. There's an I sitting there, but this thing is 2 d by dz. Okay, so here's psi in terms of f and g. All we need to do is to take the z derivative. So u minus iv. Notice that conveniently this 2i cancels with this 2i. And then we just need to take z derivatives. So what we get here, look, is z bar f prime plus g prime. And this one, we get minus f bar. What do we get from this one? Nothing, because it doesn't depend upon z. This is very important. Put a little star by anything that's important. Call that star 1. You remember this? Let's get the vorticity. Let's get the vorticity in terms of f and g. Well, remember, this is minus 4 d squared by dz dz bar. Right? We use that over there. Psi. So let me do, just so you can follow what I'm doing here, let's just do it like this. I'll take 2i out. Let's keep d by dz bar out here. And then I just worked this out, didn't I? That's all right, I've taken that. Now I just need to take the z derivative of that, which I just did. Okay, I've just substituted for psi and taken the z derivative. Now let me take a z bar derivative. Z bar derivative of this is just f prime. Z bar derivative of that is nothing. And the z bar derivative of that is f bar prime. You notice that this is just f prime minus its conjugate divided by 2i, which is the imaginary part. Okay. So omega is the minus the imaginary part, f 4 f prime. What about the pressure? It'd be nice to get the pressure in terms of f and g. We've got the velocity, we've got the vorticity. Let's look at the pressure. Well, if you recall, the pressure appeared in the original equation. Let's write the complex. Remember my arrow notation from last time, which means let's write this in complex notation. Well, del squared we know is just 4d squared by dz dz bar. Complex form of u, vector uv is of course u plus iv. What's the complex form of this? It's a good test to see if everyone's following me. Complex form of the grad P. Well, let's just do some little working over here. Grad P is, of course, the vector in 2 dimensions dp by dx, dp by dy. Complex form of that is dp by dx plus I dp by dy, which is, anybody? I like this operator, don't I? There's a plus. So what is this? Oh, yeah, but don't forget the 2. 2 d by dz bar, it's the opposite one to respect, p. Everyone getting the hang of this? We're just literally taking vectors and things in R2 and scalars and just rewriting them in terms of z and z bar. So let me put that over here to dp by dz bar. So this is just the Stokes. By the way, I could have started with this. This is just the complex form of Stokes equations. We're trying to get P though, and this is, if you like, the gradient of P. But the nice thing about this, look, is we can integrate with respect to z bar. Look, there's z bar derivatives on both sides. Right? So what I'm going to get here is 4 d by dz of u plus iv is 2p. Remember, that's what I'm looking for, p. But what else? Just integrated with respect to z bar, keeping z fixed. I've got to maybe put another function of z here. Let's call it, I don't know, h of z. An analytic function of z, remember? Because if I take a z bar derivative of this, that will give me 0. And then I get that and that. Is everybody following me? Yes, no? By the way, everything I do here, you only do once in your entire life. Then you just remember it or look it up. It's always good to see where everything comes from. See, I'm only doing this, again, to teach you. But when we get the final results, we won't need to do this anymore. It's just one of those things you do once. I've got u plus iv here, and I've got u minus iv here. So let me take a conjugate of this one. Conjugate of that is z. Okay? I'm just taking the conjugate. I'm going to need it here, look. Because I need to take a z derivative of this. So I'm going to get something from there, look. Oh, okay, let's keep the 4 there. I'm taking z derivative of that. So what do I get? I get 4 that. This one doesn't give me anything because it's anti-analytic. And then I get minus f prime. Okay, everybody stare at that. You see what I've done? I've just substituted for that. P, of course, is our pressure, and it's got to be real. H is a generally complex function, so I'm a little bit worried about that. It's an analytic function, I know that, but it's most analytic functions are complex if you evaluate them. And then over here, look, what can you tell me about this quantity? F prime bar minus its conjugate. Anything with its subtracting its conjugate is purely imaginary. So I'm a little bit worried, because this is purely imaginary, this has got to be purely real, and this is who knows what. So you can see that if I'm going to insist that P is real, you can see that H is constrained. Can anybody see what H has to be in order to make sure that P is always real? Right, let's call that 2H. It's arbitrary, we don't know it yet, and divide by 2. And move it over here. In fact, let's drop this bracket. Anybody see what H has to be? Remember, it can only be analytic. You can't have it as a function of z bar. So in other words, this f prime z bar is there to stay. I can't do anything about that. I can't use an analytic function to fix that with anything. See? So this 2f prime bar is anti-analytic. I can't fix it with an analytic. But I can change this. What do I really want this to be if I want P to always be real? I'd really love that to be a plus. So that I'd have 2f prime bar plus its complex conjugate, which would always be real. But I can always do that, can't I? By picking H to be, what is it? Minus 4f prime. Got it? So if I pick H to be minus 4f prime, that will be plus 4f prime, which will give me the what I need. So pick H of z to be minus 4f prime, which implies that 2f bar prime bar plus 2f prime z is P. The pressure. Okay? Or P is 4 I've just rewritten it. It's still 2. I've just rewritten it differently because this, of course, is the real part of f prime. So who can tell me what the pressure minus I times the vorticity is? The pressure is 4 times the real part of F prime. Minus I omega is plus I times the imaginary part of F prime. So can everybody see that this is just 4 times F prime? Because F prime is the real part of F prime plus I times the imaginary part of F prime. Okay? So this is a summary. And if you've worked with them as many times as I have, you remember all of these. That's what I've just arrived. Questions? That was okay, right? That was just a change. Yeah.
What is the physical meaning of P minus I omega?
Good question. And the answer is, as a complex number, nothing. Except it's the complex number whose real part is the pressure and whose imaginary part is minus the vorticity. You're absolutely right. These F and G themselves, well, it's just F prime. These F and G themselves, excellent question, do not have any physical significance. But combinations of them do. There they are. Okay? So the real part of F prime, which F prime doesn't have any physical significance, but its real part is the pressure. And its imaginary part is minus the vorticity. Okay? But that's a good question, because the point is we're doing a change of variables here to go to this complex plane where we've got a lot of mathematical power at our disposal. So we'll do all the mathematics there, even if the things don't have any physical significance. Then we'll take the appropriate combinations to get the physical variables. Everyone see? Now, because we'll take a break in a few minutes, just for 10 minutes, and if I imagine I'm remember we're describing Stokes flow, so you should think of honey or oil, very viscous fluids. Okay? If I took a cylinder and I dragged it through honey, it's hard work. That's because it requires a force to do that. By the way, not true over here. In ideal flow, remember before we started, that's called the D'Alembert paradox. For some reason, those flow equations I showed you earlier don't have any forces. The D'Alembert paradox. But we're in Stokes flows, and we definitely have forces. We have to drag things through viscous fluids. In other words, there's always forces and torques we need to worry about. So let me just comment on that. And I might say more about this next week. One of the reasons I'm not spending too much time talking about them here is because the first thing I want to focus on is low-Reynolds-number swimming. And it turns out that low-Reynolds-number swimmers move by virtue of the fact that they don't exert any force or torque. But most things do in Stokes flows. So I'm going to set these as exercises. And by the way, next week I'll give out the notes, probably just printed notes of everything I'm saying. But you should try to do these as exercises. So I'm going to use the results, but you see all these calculations here? That's what you have to do in these exercises. So let's call this exercise 1. If you're a fluid dynamicist, you will have seen this tensor before. It's called the rate of strain tensor. Rate of strain tensor in fluid mechanics, and it turns out that you can show, this is the exercise, that E11 plus I E12 is ZF bar bar prime bar try that for yourself. You should be able to do that now. It's just the first diagonal and off-diagonal elements with an I added is this particular combination. So what I'm imagining here is I've got some curve, and there's a tangent and a normal, and ds is just some arc length element of the curve. This, you should think of this as perhaps some just curve in the fluid, and then you can work out this, which is the stress tensor. Well, the stress. This is the stress actually. This is the stress on some curve here in terms of the normal, and you can use this result here and the pressure which we got here to show this. I always find this quite interesting. Because look, this function h turns out to be very important here. The stress on the boundary is just a total s derivative, an arc length derivative of this function h, and h looks very similar to the velocity field look. If I took a conjugate of that, oh, hold on, sorry, there was a typo here. There should be a bar there. Sorry about that. If I take u plus IV, it's basically h. The only difference is there's a plus sign here. That, by the way, is very useful mathematically, that observation. By the way, I strongly encourage you to try these exercises because it will make sure you've understood what we're doing here. it's just rewriting everything in complex notation. And as I said, it's something you do just once in your life, and then you see that it's true. So,
my question is that this formula indicates the force that depends on the direction of the curve.
yes. Yeah. Oh, yeah. So this is the outward normal. Oh. So we're going in the usual anti-clockwise direction.
We pick on a curve.
Yeah. You pick. Yep.
Then we can define the ds.
That's right. So this is on. So this is the fluid stress on a curve.
At some point.
Yeah, at some point. And in particular, look, you can now work. Suppose it's the boundary of an object. Then you can work out the total force on the object. That's what we're going to do in exercise 3. Exercise 3 is show that the total force exerted on the fluid by some object with boundary curve C, say, is, well, you can see, look, it's precisely by definition. You go around C and you add up the stress. This is the complex force. This is, oh no, this is the actual force. You know what I'm saying? Let me just do it like this, Fi. Well, can you see what the complex form of the complex force is? This is another beautiful result. I've just shown you from exercise 2 that at each point in the fluid where there's a normal vector n, then it's this in complex form. So in order to work out the total force around the curve, you have to integrate this with respect to s. So it's the integral of a total derivative. So in fact, it's 2I times the change in h as you go around the curve. Because I'm integrating a total derivative. So if I put, this thing is just 2I dh by ds by exercise 2. Okay?
What means the matrix of EIJ, eigenvector and eigenvalues?
Oh, they're known as the principal rates of strain. If you take this rate of strain vector and diagonalize it, is that what you mean? See, this is symmetric,
Yeah.
so you can diagonalize it, as you say. People call those the principal rates of strain at a point. Okay. Yeah, at any point in the flow, there's a rate of strain tensor, and you can diagonalize it locally. And then the two eigenvectors are perpendicular, and they're the principal rates of strain. People study those in turbulence. Here we don't diagonalize. We don't diagonalize here. We just notice that this combination is this. Any more questions? We'll take a break. We'll take a 5-minute break now. Any more questions before I go? Wash my hands.
This is the same situation as in the compressed fluids, meaning some sort of distribution of the seniority that some force.
Yes.
That doesn't depend on any shape of curves.
Oh. depends only on the change of h as you go around the curve. But don't forget, h isn't analytic or anything. That's why I made sure to put ZZ bar. So you have to be careful with Cauchy's theorem. Okay. One thing you can conclude is, suppose f and g are both single valued in some region of the fluid, and you draw a curve, then what's the change in h as you go around the curve if f and g prime are both single valued? Well, look, if f and g prime are both single valued, then this is single valued, derivative is single valued, and this is single valued. So there won't be any change in h, and there won't be any force, net force on that curve, the fluid in that curve. Okay, let me take a break, and then I'll just say something when I get back about torques. Okay, let's continue. So we got a lot to do. Okay, let me just review these exercises. This is the definition of the rate of strain tensor. What I want you to do is use what we already know what U is in terms of F and G. So you should be able to show that this particular combination of the rate of strain components is this in terms of F and G. Okay? You can then also show, now that you know what this is, you know what the complex form of this is, the normal, you know the complex form of that on a curve. Let's just check you do know that. So look, here's a curve. Suppose that's the tangent vector, unit tangent vector, and this is the unit normal vector. What's the complex form of the unit tangent? On the curve. So the tangent on the curve is like dx dy, the little unit, the components of the local tangent to the curve. So this is going to be dz over mod dz, because it's the unit tangent. And we're calling dz, by the way, the modulus of dz is ds. That's the little arc length element. So this is dz by ds. Want to see? So what's the complex form of the tangent, the unit tangent, the unit normal? How do you rotate by 90 degrees, minus 90 degrees in complex variables? You multiply by minus I. So the normal, unit normal, goes to minus I dz by ds. Okay? So you're going to need these when you show this. You already know what pressure is in terms of F prime. Remember, that's the real part of 4F prime. You use exercise 1 here, and you'll be able to show this. That, by the way, is probably a page of algebra. But it's worth it because you get this beautiful result that it's a total derivative with respect to S. Okay, you can see where the derivatives come in. Look, because when I put n in here, I've got ds's in the denominator there, so you can see that I can patch it all up to be a ds derivative. It's worth doing, so you can see why it's true. And then this exercise 3 is a beautiful result, which tells me if I've got a closed curve in the fluid, and then I integrate the stress around it, that gives me the total force on the fluid, or with a minus sign, force on the body, and it's just the change in h as I go around the body. That's the total force. I've made a note here, look, that if F and G prime are single valued as you go around a body, if F single valued, its derivative will be single valued, which means that H, that's single valued, Z is obviously single valued as you go around, this is single valued, and by assumption this is single valued, then H is single valued, and it means there's no force, no total force. So that's very convenient, because in order to impose conditions that there's no net force on something, you just have to make sure that F and G prime are single valued. So that's very nice. I don't even have to work out any integrals, I just make sure F and G prime are single valued. Torque, by the way, so suppose, remember, when you take the torque, you basically, you take x minus some point and you cross it with the force. Normal torque about some point. Right? Normally, if you've got some x naught here, and there's some position x, the torque is x minus x naught cross, suppose that's f at that point, cross f. That's what you mean by the torque. Torque at that point, and then you want to integrate that if you go around a whole curve. Remember the other day, I told you what the cross product is in complex form. Remember that? Remember when I derived what the dot product was? I took the real part of A bar B. The imaginary part was the cross product. So you're going to need to use that. Okay? And you'll get this formula if you take x naught to be 0, which I've just done for simplicity. Okay? Does everyone have clear about what you should do in principle for these exercises? You see, I could have gone through all of these on the board, but it would have taken an hour. And I'd rather do some other things. But I'm going to use these results. And, by the way, if you have any trouble showing these, come and speak to me, I'll show you. Right. We can start solving things. Because we've done everything. We've done all the background.
Depends on the shape of the curve.
What was that?
Torque depends on the shape of the curve.
Yes. Yeah, because don't forget, you're adding, it's not like, remember, you have to forget about Cauchy now. You can't, change contours and you still get the same answer. Because remember, we've lost a lot of analyticity. We've still got analytic functions here, but we've lost a lot of analyticity. So the force, if you take a curve in the fluid and want to work out the total force around it, and then you change that curve to something else, it's not necessarily going to be the same. Just remember that. A lot of your intuition from ideal flows is to do with Cauchy. But that's because there's just analytic functions everywhere. But now we've got these z-bar things in the general solution. That's anti-analytic. Right. Let's just make sure let's just get some intuition about F and G then. So let's do let's find F and G. Let's do an example. Let's find F and G. Find F and G prime, say, for we want shear flow. Shear flow. Yeah, simple linear shear. Simple shear. So UV is UY0. Okay, so it's just this. Haven't seen this before, right? Simple shear flow. So, U is some constant. Okay, so it's shearing flow in the plane. Okay, let's do this. Well, what's U minus IV? U minus IV, in this case, is that, is U minus 0. That's it. But of course, Y, we all know, is Z minus Z bar over 2I. That's the shear flow. So but we also know that this is related to F and G like this. So, we need to identify F and G. Can anybody tell me what either of them are? We've got to equate this with this and identify F and G prime. Well, the first thing I notice is that this is anti-analytic, and this isn't anti-analytic or analytic. It's a mixture. All I can say about this is it's a regular function. But look, this is an analytic function. And the only analytic function I've got here is G prime. Does everyone see? So I'm going to set G prime. There's only one way to do this. G prime to be minus IUZ over 2. So that this is the same as that. Can I see? Right. Now, this thing, which is the anti-analytic thing, has to somehow equal the rest of it. Now, let's stare at this a little bit. Remember, this is the one that seems to be causing a problem because it's not analytic and it's not anti-analytic. Whereas this is anti-analytic. So I'm thinking to myself, the only way that I'm going to be able to do this is if I take f prime to be of z to be a constant function. If f prime is constant, this is then purely anti-analytic. That's going to be purely anti-analytic as well. So in other words, let's let f of z be alpha of z. Remember, it's got to be an analytic function, but you can see then that f prime will be alpha. And f of z bar will be alpha bar z bar. So therefore, minus f bar plus z bar f prime is minus alpha bar z bar plus alpha z bar, which is this. Right? So we want this thing to be equal to IU over 2. See? If this is my answer, this is my guess, which implies this and this, I've then substituted this thing is just this thing. And that better be, and by the way, if you substitute these, you just get this, and then I want that to be that. So alpha minus alpha bar better be IU over 2. So this is equivalent to saying that if we divide this by 2I, it's the imaginary part of alpha. So the imaginary part of alpha, if I divide it by 2I, is U over 4. See? So therefore, take that'll do it. Everybody follow that? Just trying to find the f and g prime. I knew, by the way, before I started, that shear flow is a solution of the Stokes equations. So I knew, therefore, that f and g prime existed. And I just found them. Let me just do another example. Suppose you've got a channel. People call this Poiseuille flow through a channel. So UV is the following. Okay, so this is height. This is unit distance. Poiseuille flow for a channel. It's got to be no slip on the boundary walls. These are solid boundaries. Here it is. It's got this parabolic profile. Let's find f and g. So u minus iv is uy1 minus y. That's it. V is 0. So this is u z minus z bar over 2I. And this we've got to equate with the same thing we did over there. You can see it's a little bit more complicated. I'll expand it out for you. You just get 2I. See what I've done? I've just multiplied up by 2I there, taken out the 2I squared, which is minus 4, and then expanded out this, and this. Okay? Who can tell me what G prime is? Because this thing is equal to this thing. So let's identify you can usually spot G prime because it's the only analytic thing. So look, it looks like that's going to be part of it. That's not. That's not. That's not. Must be these two. So minus U over 4, 2IZ minus Z squared. What do you see? What about F? Not quite so easy to find because remember you've got this funny, you've got to equate these two with what's left. So that's gone and that's gone, but you see this, and this somehow have to be the same as this. Let me just tell you how I would do this. I notice that so looking at this term, and this term, and I notice it's quadratic in Z and Z bar. That's quadratic in Z bar, so that's linear, in fact. Okay? So what I'm going to do is I'm going to try F to be quadratic. And it can only be a function of Z. So I'm going to let it be ZZ plus beta Z squared for some alpha and beta to be determined. You see why that's a natural thing to try? So of course that means that F prime is, 2 beta Z plus alpha. You can finish this off, and I'm not going to do the details. And what you find is that alpha is IU over 4, and beta is minus U over 4. Okay, so that's F. Anybody got any questions?
Excuse me. There is one Z is uniquely determined.
Good question. No.
Oh. Yeah, real part of it.
Yeah, remember over here, I deduced that the imaginary part of alpha was U over 4. But I didn't determine what the real part of alpha was.
So different flows.
Let me show you. Good question. This is just an aside, although it's a very important one. Thank you. Let me just look at the following. Suppose f of z is, what should we call it? Lambda z, where lambda is real. What's for f prime? Well, f prime is lambda, so 4f prime is 4 lambda, which is real. Now, what was 4f prime in terms of the physical quantities? Remember? Plus minus I omega, remember? Right. Now, this is purely real. So what's the vorticity associated with this flow? 0. Because look, so this implies that P is 4 lambda, omega is 0. This is real. So P is that, and then the imaginary part is 0. Okay? You understand? I think I might have confused you. What I'm trying to show you here is that, remember, the equations we started off with was del squared U is grad P. Grad P, not P. And the point is that Stokes flows, as with any flow, is only determined up to a constant pressure. You can add a constant pressure to the pressure field. Okay? And this shows up in the F and G in the fact that to any F, you can always add a real multiple of Z to get uniqueness. Okay? Or rather, there's a non-uniqueness up to this lambda. And what I'm showing you here is that lambda is precisely this indeterminacy of the pressure. Okay? You understand? What I'm trying to show is that the equations we started with don't give me a unique pressure. I can add 10 to the pressure and it's still the same flow. Everyone understands? You know, when you read papers on fluid dynamics, there's a bubble, say, in a flow, they say, oh, let me set the bubble pressure to be 0. They do that because they've got this freedom to set the pressure somewhere. Up to a constant. And hence, you see, don't forget, it's F prime that's related to pressure, which means that F is only determined up to a real multiple of Z. And by the way, in this problem, remember, the imaginary part of alpha was U over 4. If I'd added a real part, it wouldn't have mattered. So your good question is not unique. F and G are not unique, but it corresponds to the indeterminacy of the pressure. Any other questions? Yeah, good question, thank you. By the way, there's actually another freedom. Can anybody see this? Very good. So the point is that we can set the pressure at some point in the flow to make F and G unique, plus, let's look at the velocity field. Look at this. Can anybody think of something I could, suppose you give me an F and a G that for a given U and V. So in other words, U and V are given, and I found some F and G for which this is true. Can anybody think of something that I can do to F and G that will give me the same velocity field? Well, how about this? Suppose, oh, I better not use that notation. Suppose F goes to F plus C, some constant, and G prime goes to G prime minus C bar. Sorry, plus C bar. You see? First of all, F prime will be the same, so this will be the same. But if I subtract C bar from this, and then add it back in with this one, it doesn't change the velocity field. Okay. So very good question. I didn't want to spend too much time on this because basically there's freedoms to do with adding a constant to F and G in this way and adding these basically pressure fields to these linear functions of Z to F to make it unique. But it's an excellent question. I didn't want to spend too much time on that. It's true, and I'm glad you pointed it out. And textbooks tend to spend pages and pages on this. It's just the fact that there's a kind of these degrees of freedom in the Gaussian functions. I'm happy? You have to be aware of these, by the way, when you're trying to solve a problem. Because you need to set these to freedoms. Okay, I wanted us to do a non-trivial, before we go, I wanted to talk about microorganisms, but before we do that, since we're in Japan, I found a fantastic problem that we will do to show you how F and G work, and it's a new way of approaching it. In fact, I included this in a paper of mine a few years ago. But the original person to solve this problem was Hashimoto. Do you know him? He's in Tokyo somewhere? So this is example 3. We're going to do a problem that Hashimoto. If you guess how long ago? (1958). So this is quite a long time ago. And what he considered, and this is a great problem given what I told you last time. He considered this problem of pressure-driven flow through a gap in a wall. Okay, so this is like these are kind of two plates, but there's a slit between them. And what you're trying to do, so in fact, let me, basically I've got two flat plates like this, and I'm forcing flow between the gap, and these go on infinitely. Okay, and there's a higher pressure here than there is down here. So what's happening is there's a pressure gradient from up there to down there, and it's forcing flow through the gap. Now, Hashimoto did not do it like I'm going to show you. He did it using different considerations. But I'm going to show you how to do it my way. Do you recognize the geometry? Remember yesterday or Tuesday, I was talking about this point vortex, wasn't I? In fact, I mentioned it earlier today, and the gap in the wall. How did I tell you you should solve that problem? Using conformal mappings. Did everybody go on Wikipedia Tchaikovsky? See, there's a page on it, right? Hashimoto didn't do this. He didn't use Tchaikovsky. I'm going to solve this problem using Tchaikovsky. Right. So let's set up the bound. We've got to find F and G. You see, Hashimoto didn't even introduce F and G. He did it a completely different way. So must find F and G prime. Okay, and then we can integrate to get G if we care. Okay? So what we've got here is, let's suppose that the pressure up here is delta P, but then it's minus delta P down here. What I'm doing? Oh, yeah, no. Let's take it to be delta P over 2 and minus delta P over 2, so that delta P is the pressure difference. Okay, so there exists a pressure difference delta P between, let's call it infinity plus and infinity minus. So up here is infinity plus. So there's a pressure drop, and it's going to force a flow through the gap. Okay? So this is the problem. There's a pressure-driven flow through here with a pressure drop grad delta P, and the pressure tends to this value here, and the minus of that there. Okay, so in particular, this implies 4F of Z. No, let's take the 4 over there. Tends to grad P over 8 minus grad P over 8, del P over 8. And G prime, by the way, tends at worst. Well, actually, let's do this. Let's add some constants here. Yeah, we'll call it F naught plus and F naught minus. And then G prime tends to some constants. Okay, so these are, if you like, what we call the far field conditions. It's what's forcing the flow. What's the other boundary conditions? This is a viscous fluid being forced through a gap in a wall. Here's the wall. What's the boundary condition for a viscous fluid on a solid surface? No slip. It's the no slip condition. Viscous fluids cannot slip on solid surfaces. Okay. So, on the wall portions, we have no slip. And that means U minus IV is 0. Okay. Now, you see, I can't, actually, I haven't looked at Hashimoto's paper for a while. I can't remember exactly what he does. But he doesn't use conformal mapping. I'm going to use conformal mapping. And the other thing you need to be careful of, and we're going to see this next week, what about these corner points? See, whenever you get a corner point in a flow like this, you've got to be suspicious that there might be some singularity at the corner point, the functions f and g. In fact, lots of people have studied this. The person who I most equate this with is Keith Moffat from Cambridge, who studied what he called Moffat eddies. And the point is, he was interested in what do Stokes flows look like near corner points. And this is like a corner, but it's got an angle 2 pi. So it's a corner of angle 2 pi. And we're going to see that next week. We're going to look at these Stokes closing corners, which is what Moffat did. And we're going to see that it turns out that F and G have square root singularities there. So we've got to expect square root singularities from a local analysis. I'll show you the local analysis next week. Hashimoto knew that. And in his solution scheme, he built in the fact that F had to look like that far up and that far down. It must have square root singularities at the corners, and it must satisfy the no slip condition on the edge. He didn't even think about F and G. He was thinking about the velocity field. So the velocity field has square root singularities there too. Let's do it our way. So we're going to use conformal mapping. Now, the first thing I want to warn you is that most people don't think you can solve Stokes flow problems using conformal mapping. The reason is because I think it's the experience with ideal flows. The problems I showed you with ideal flows are what we call conformally invariant boundary value problems. These aren't, but we can still use them. Everybody remember how I constructed the mapping? We're going to do it. I'm going to map from a disk. So introduce a zeta disk. A parametric zeta disk. So here it is. It's a unit disk in the zeta plane. Now, Joukowsky told me that I can map this to this. If I let eta be, that's the Joukowsky map. Well, that's not quite our domain. This is our domain. And we know how to do this last part. We're going to do an inversion, which is also an analytic map. So what we're going to do is z now, which is our final variable, is 1 over eta. And then, as we discussed last time, this 0 point goes to infinity, and this whole portion, nice portion here between 0 and 1 goes to 1 to infinity. What happens is, so this is our final domain. Notice, look, eta can be written as zeta squared plus 1 over 2 zeta. So 1 over eta, z, is that. Everybody understand? Let's just study this a little bit. What do you notice about that function, z, as a function of zeta? Two zeta over zeta squared plus 1. Well, it's a rational function. What are its singularities? Plus or minus I. Right? So in other words, here and here at I and here at minus I, it has singularity. Guess which point this corresponds to in the z plane? You did the right thing. You pointed up and down. You don't know which one. But the beautiful thing is the following. This point corresponds to up here, infinity plus. And this one corresponds to down here, infinity minus. And this is great news, because remember, we've got different things happening at infinity plus and infinity minus. So it's very nice that our conformal geometric approach is kind of separating the point at infinity to be kind of an upstairs infinity and a downstairs infinity. So that's very useful. Okay. Let's just check, by the way. Let's imagine what happens if we come in here, look. Suppose we come in like that. So in other words, let's just do some little work over here to check. Let's suppose zeta is I 1 minus epsilon, where epsilon is positive and small. See? So as epsilon goes to 0, I'm basically coming up here. Let's look at what happens to z. Well, let me factorize it. Okay? Then this is, we substitute this, it's 2i 1 minus epsilon divided by this one. What's this one? Isn't it I 2 minus epsilon? And then this one is I minus I epsilon minus I. So this one's minus I epsilon. Everyone see? Did I do that right? So look at what happens as epsilon gets small. As epsilon gets small, the top looks like 2i. This looks like 2i. So it looks like 1 over minus I epsilon, because these are the same thing. So in other words, it looks like I over epsilon. Now epsilon is positive and tending to 0. So what's z doing as epsilon gets small? What I'm trying to say is, as I move up that little arrow, where am I moving here? Up the imaginary axis, the positive imaginary axis. So in other words, moving up there is equivalent, moving up here is equivalent to moving up here. Okay, so I've got this nice analytic identification between the physical plane and the disk. Let's just make that explicit. Note that z I'm just writing this slightly differently, and actually a little less correctly. What I'm doing, I'm just looking at the local behavior as zeta tends to plus I and zeta tends to minus I. And the point is, z looks like this near there and this near minus I. Now, here's where the magic comes. I'm looking for an analytic function f of z, where f of z is analytic here except that it's got these. Hold on a minute. You should have corrected me. Look, when I integrated this, I should have put z's here. I hope you noticed that. I just integrated this. And I divided by 4. Okay. So look, here's what we have to find. We have to find some function that's analytic everywhere outside here, having this behavior far away, upstairs, and this behavior downstairs. So here's what I'm going to do. I'm going to introduce capital F of zeta, which is going to be the kind of composition. Think about this. Think about zeta in the disk. Zeta is an analytic, this function z zeta here is analytic inside the disk, strictly inside the disk. It's not analytic on the boundary. Of course not, because it needs two singularities to go to plus and minus infinity. They're there and there. But inside it's analytic. So every point in here is analytically mapped to these points. And then f, we know, is also analytic. Little f of z is analytic in here, except for simple pole singularities at plus and minus infinity. Want to see? So in other words, this is analytic strictly inside the disk, with singularities at zeta is equal to plus or minus I of known form. In fact, let's write them down. Who can tell me what the behavior of these things is as zeta tends to plus I and as zeta tends to minus I? Well, look. Z tends to infinity plus is zeta going to plus I. And F goes like delta P Z over 8. But as zeta goes to plus I, Z goes like this. So what does F of zeta, which is F composed with Z, go like as a function of zeta? Well, watch me, everybody. It goes like delta P over 8, that's just a constant, times Z. But Z goes like this, I've just determined. So in other words, F of zeta goes like this. Everybody with me? Now, let's go downstairs. As zeta tends to minus I, which means Z goes to minus infinity minus, F goes like that, but now the same thing with a minus sign. And Z goes like this one. Is everybody with me? So I get the same thing here, but now with a minus sign, delta P over 8, 1 over zeta plus I. Does everybody follow me?
What about the F0 plus minus?
Oh, yeah, plus. Actually, let's put plus F0 hat twiddle, because we don't know it's the same constant, because this is the leading order behavior. We might have some different constants. Whatever, constants. Is everybody following me? I want you to understand this because I've nearly finished the problem. I've nearly finished. And this is the beauty of the complex analytic formulation, is that if you think about these problems geometrically, the answers often just stare you in the face. And what's nice about this is Hashimoto had to worry about these square root branch points at the edges. There's no square roots in this. We'll see them later. But we're going to get the solution in terms of zeta now. Watch the following thing, which is very beautiful. Look, Z, which is that thing, looks like this as zeta goes to plus I and minus I. 1 over zeta minus I, 1 over zeta plus I. The F that I need to find is almost the same thing. Delta P over H is constant. The only difference is the minus sign. It's the only difference. So in other words, that thing looks like that, which is almost the same as what I need multiplied by delta P over 8, except there's a minus sign that's wrong. What can I do to that to make sure that when I go to plus this one, I get a minus sign there? Can anybody see? This thing looks like that. It is not quite what I want because there's a missing minus sign in the bottom. Can anybody see how to slightly change this to make the minus sign appear here? I'm going to let you stare at it because this is the essence of the formal geometric approach to these problems. It's completely different to what you see in the literature. It's more geometric. What about this? Look, notice that the top has got a zeta in it. And zeta goes to plus or minus. So I wonder what the function, what if I just take this function, but I remove the zeta from the top? Right? Let's just do this one. I've just removed the zeta and the 2. I don't care about the 2. What does this tend to? In fact, let's keep the 2. No, let's keep this together. As zeta tends to I, this thing blows up. But what does 1 over zeta plus I tend to? 1 over 2i. So this tends to 1 over 2i zeta plus zeta minus I. What about the bottom one? Well, then this thing blows up. And this thing tends to 1 over minus 2i. So this tends to minus 1 over 2i, zeta plus I. Aha! This is exactly the behavior I need. But F. Everybody see? You okay? See, look, all I've done is for the top one, this is the singular bit, and then this tends to 1 over 2i, because as zeta tends to I, this goes to I plus I. 2i. And then down here, I'm doing this. This is singular, which is there, and then this thing, as zeta goes to minus I, goes to minus I minus I, which is minus 1 over 2i. That's almost exactly what I've got here, except the factor's different. But let's fix that. Here's our guess. Well, we need to get rid of the 2i. And we need to multiply by delta p over 8. And it's this. Is everybody with me? We need to check though. F is analytic inside the disk with singularities at the edges. We fix the singularities to be correct. Is it analytic? Is our guess analytic inside the disk? Yes. And it satisfies the requirements on the plus minus I. It is in fact the correct F. You see how I did that? I hardly did anything. I just looked. Now, what's G? By the way, you haven't even seen the best bit. The best bit's coming up now. I found F. What's G? Notice this, look. I'm rubbing this out because we know this. Have we imposed this yet? No. How can I? We haven't even imposed the boundary condition yet. But look, what's U minus IV? Well, I'm going to, like f zeta, I'm going to introduce capital G zeta. Now, on the wall, U minus IV is 0, that's the boundary condition, and that's equal from this to right? That's just F bar. What's F prime in terms of capital F? I know capital F is this, so what's F prime in terms of capital F? I have to use the chain rule. Because this is df by dz. So it's, let's call it F prime of zeta divided by Z prime of zeta. df by d zeta divided by dz by d zeta. That's df by dz. Plus G. By the way, this is true on the wall. What does the wall correspond to now in my zeta domain? I've rubbed it off, haven't I? But it was the unit disk. Right? The unit disk maps to the walls. Maps to the walls. That's the whole point of the conformal mapping. So look at what this tells me. This is a beautiful thing, but on the wall, z bar is 1 over zeta. Because, you know, that's the wall. Hence, look at this. See, look what I've done here, look. This is slightly subtle. There was a z bar there, but remember, I'm thinking of z now as a function of zeta. So z bar is the whole, is z zeta barred, but then that z bar of 1 over zeta. Right, that's what I've got here. That's z zeta bar, which is z bar zeta bar, which is z bar 1 over zeta. That's where I got this from. And this is from the chain rule. Now here's the beautiful thing. This is now a relation between analytic functions. This is analytic function zeta, analytic function zeta, analytic function zeta, analytic function zeta, analytic function zeta. It's a relation that holds on the unit disk, and by the beautiful principle of analytic continuation, it therefore holds off the disk. And therefore, if I know F, this tells me that G is this other thing. Oh, sorry, this should be minus that. So, in all the boxes on the board then, is the entire solution. Z is related to zeta like this, that's the conformal mapping. F we deduced was this, and there's G. Notice, by the way, the appearance of the conjugate, Schwartz conjugate of F here in G. That's it, that's the solution. Isn't it amazing? Isn't it amazing? And I remember, I derived this for myself because somebody asked me what the solution to this problem was. And it's only later that I looked up Hashimoto's paper. And of course, it's not written in this form at all. And I then had to rewrite this in terms of Z and show that it was the same as his solution, which was written, I think, in terms of X and Y. I can't remember. And of course, he's got square roots in there. Where are my square roots? What I love about this method is that I never see a square root. And yet I've got the solution. Where does Hashimoto's square roots come in? By the way, can I just emphasize before I will answer that question? Did you see how beautiful this was? The only real trick here was just spotting this simple thing. And then G was automatic. Square roots, where are they? remember, Hashimoto didn't introduce zeta at all. So in his solution, zeta doesn't even know what that is. So let's go to my box here and write zeta in terms of z, which fortunately I can, because look at this, I can invert that for zeta as a function of z, it's just quadratic. What is it? Zeta squared plus 1z is 2 zeta, which is zeta squared z minus 2 zeta plus z. It's quadratic for zeta. Aha! Which route do I take? Well, look, zeta tends to 0, z tends to 0. So this tends to this point, which means that as I take z tends to 0 here, I better have this tending to 0. So I'm on the same branch. So which sign? Z tends to 0, look, that tends to 1, and I've got a 1 there, so I better take the minus sign. There you go. This is z. Zeta is a function of z. And look there. These are the square root branch points at the edges of the gap. And if you take all of my formulae and get rid of zeta, you'll get Hashimoto. You could do that as an exercise and look up the 58 paper. It's in the Physics Society of Japan, Japanese Physical Society. Any questions? Okay, we'll take a 5-minute break. Maybe we'll set the computer up. Maybe we'll set the computer up when I get back. For example, this Hashimoto problem, you can also solve it using what they call Riemann-Hilbert methods, which is where you have analytic functions that jump across a contour. So the wall here is, in a sense, a contour across which an upper and a lower analytic function jump. Another way to do it. By the way, let me remember, if you were interested in seeing more details, I did basically everything you need to know on board. But if you want to, I actually published that result, pretty sure, in the Proceedings of the Royal Society, Crowdy and Sampson. It was, I think, 2010. 2010, something like that. It's got something like gaps in the wall in the title. I can't remember what it was. But the reason we rederived it is because we wanted to solve different problems. We didn't want pressure-driven flow through the gaps. We were interested in what does a low-Reynolds-number swimmer do near a gap. And the point was, it's not at all clear how to generalize Hashimoto's analysis to that case. Because now you've got your wall with a gap. So in other words, remember, I showed you the vortex problem. What does a vortex do near a gap in a wall? That was solved in 2004. But if you've got a little low Reynolds number swimmer, What does that do near a gap in the wall? And certainly nobody had studied that problem. So that was why we ended up thinking about Hashimoto's problem in a different way. But let me give you more background now, because I'm going to talk about singularities next time probably, or I might start today if we've got time. I'm going to start talking about singularities of the Stokes equations. So last time when I introduced ideal flows, I introduced the point vortex. Okay? That's something that people do in ideal flows. That's a basic kind of paradigm to model vortical flows. And there's analogous singularities for Stokes equations. I'm going to list them all and derive them all for you, maybe later today, if not next time. Now, I'm going to talk about microorganisms here. So you should be thinking about maybe a little bacteria, very small bacteria in a slow viscous flow. It's okay. Thank you. All right, yeah. You should be thinking about bacterium, maybe sperm. By the way, there's in fertility science, there's a huge amount of activity in understanding low-Reynolds-number hydrodynamics, because people want to understand how to promote fertility. How do you make sperm propagate along a wall? What any low-Reynolds-number swimmer, I'm going to call it a low-Reynolds-number swimmer, or microorganism, so I'm kind of encapsulate, this term means any of these things. And by the way, people even build little micro-robots, their own little swimmers, to do particular things that they need. Some cargo carrying along a microchip, for example, in microfluidics. People are trying to control these things. And the whole point about swimming, low Reynolds number, and I haven't put it on this slide, but Purcell, I think it was about in the 70s, he wrote a fantastic essay that everybody cites. He's a physicist who got interested in low Reynolds number hydrodynamics, and he wrote a fantastic article explaining the essence of low Reynolds number swimming. It's on the internet. Just Google, Purcell low Reynolds number, or Stokes law, some swimmers. You'll see it. And it's only a few pages, but it's fascinating to read. And what he basically tells you is that when we go swimming, we basically propel ourselves through transfer of momentum. But a low Reynolds number swimmer doesn't do that, because we've set the Reynolds number to be 0. So if anything, momentum diffuses now. We've kind of got a del squared U. Not quite 0, it's grad P. But basically it's a more diffusive process, so there's no inertia anymore. And because of this assumption that the Reynolds number is so small, what a low Reynolds number swimmer does is it does something. It either moves its body in a particular way, it's surrounded by fluid, it moves its body, or it doesn't change its shape, but it's got little cilia on its surface that kind of move in waves to create a surface velocity. Basically, it does something to create a flow around it, a Stokes flow around it. And the constraint is that because the Reynolds number is 0, there can be no net force or a net torque on that body. Okay? And it's those constraints that perhaps imply a locomotion, either a translation or a rotation. So the condition that there's no net force might imply that the thing has to move in a particular direction, and the fact that there's no net torque might mean it has to rotate. Okay? But it's very different to us deciding, if I want to swim that way, I'll do some kind of breaststroke to make sure that there's momentum this way so that I go forward. It's not as explicit as that. The swimmer does something to create a flow around it so that indirectly the total force and torque on it is 0, and then it might move in this direction or that direction. It's very much more indirect. Okay? But that's what makes it such a fascinating subject. And in fact, a lot of physics people who study colloids and kind of Janus particles and things like this, there's lots of chemical processes going on at these small scales. They don't even understand why things move in a particular way. what is the physics that's making it do that? They still don't understand that in lots of cases. So it's a fascinating subject that's huge at the moment. Microfluidics, nanofluidics, biomechanics, fertility science, colloid science, all of these areas are all interested in the same mathematical problem. If I've got a little swimmer that does something, how does it move? And to do that, to find that motion, you have to solve the Stokes equations. Okay? Right, let me tell you how I got interested in this. Here's a famous fact. By the way, Lord Rothschild was in Cambridge in the 50s, and back then, that was when people started to get interested in this. People like Taylor, G.I. Taylor, wrote a famous paper in the 50s, which has become famous, on swimming sheets. And Rothschild was doing some experiments. Here's what he did. He took 2 glass plates, and he put some viscous fluid in it with, you see these? That's sperm cells. It was actually from male cows, right? Bull sperm. And he put them with some viscous fluid between 2 plates, and he just let it go. And later, he looked, I presume under some kind of microscope, at what the density of where the sperm had gone later. And here's what he found. These are the walls. And this is the number density. What you see very clearly is that these sperm are attracted to the walls. Okay? And it's kind of a well-known fact since the 50s that for some reason low-Reynolds-number swimmers tend to get attracted to walls. Okay? Right. And so that was something that I actually knew. Oh, not that one. And here's an argument that was actually only put forward recently. And the argument was basically, remember, these little organisms are very stupid. They don't have any neural networks or anything. They're just little organisms that do a particular thing. So they never decide to do anything and make it happen. It just happens. And one of the things we're going to see is that here's a sperm, for example, and it's got a head, and it's basically got some actuation of its tail. So that what happens is there's basically a force in this direction due to the motion of the tail, and then a drag in the direction of this is what they call a puller or a pusher. I think this is a puller, isn't it? I'll remember in a second. So we've got a plus force and a minus force that total to 0. So there's no net force on this object, and mathematically, plus minus point force gives you what people call a stresslet singularity. Okay, we're going to see all this in detail, probably next time. And it's known that and stresslets have a direction. Okay, and if you're near a wall, you can show that stresslets tend to get attracted to walls. So in other words, remember the method of images that we discussed last time? Look at this, by the way. You can see that in Stokes flows, the image system is a lot more complicated than we saw for the ideal flows. So if you've got a stresslet here, it tends to get attracted to the wall. Okay, so that was just a basic argument that essentially, if you're modeling a low-Reynolds-number swimmer as a stresslet, it can't help but get attracted to the wall. But that's not how I got involved, because I went to, this is how I got involved. I visited Caltech in 2009. And this chap, Yizar Orr, he was also visiting. And I saw him give a seminar on this. And here's what he was doing. He was putting little, this was a numerical experiment, and he was putting little spheres connected by rods, here's 2 spheres with rods, near a wall. And look what he was doing. To create a flow around it, he was saying that this sphere rotated with some angular velocity u1 that he specified. This one, some angular velocity u2 that he specified. And this rod made sure that the whole thing stayed together. And numerically, he solved for the Stokes flow around here, and insisted that the whole structure had no net force and no net torque on it. Okay? So these angular velocities are the actuation mechanism, and then the constraints that it's got no net force and no net torque, that implied that it has to move in a certain way. Okay? Everybody understand? That's the essence of low-Reynolds-number swimming. No force, no torque implies velocity, angular velocity. Okay? And here's one of the things he noticed. For certain regimes, the thing moved away from the wall. So this is a simple artificial swimmer, but he found situations where it could move away from the wall. He found lots of things. By the way, he tried lots of different swimmers, and this was all done numerically. Numerical experiments. So he solved, at each instant, he solved the Stokes equations, enforced zero net force, zero net torque, and then time evolved. It was quite a intensive computation. Here's something else he noticed. Look at this. This is one of these swimmers. He calls it a 2 plus 1. Two are actuated. This one just sits there. And here's what he did. He noticed, look, for a period, this is actual video shoots. It moves away from the wall, but then it reorients, and then moves towards the wall, moves up again, and eventually settles down until it's in a steadily translating state along the wall. Okay? And these are some face portraits. So this is with y, distance from the wall against orientation, and it settles down to this stable point. And this is, what is this? This is time against orientation. So what happens is, after a sufficient amount of time, it stays in a particular orientation and just travels a constant speed along the wall. Everybody understand? What else did he say? Now, you see, look, this was fascinating to me, because this appeared in 2010, I think. 2009, 2010. But then I was reading the Journal of Fluid Mechanics, and people were studying sperm near a wall. And they were doing numerical calculations again. Look at this picture. This is this picture by my colleagues with spheres and rods. Very artificial swimmers. That's the trajectory. This is the trajectory if you've got little sperm with long tails and ellipsoidal heads. And they were solving these Stokes equations using all kinds of clever boundary integral methods to solve for this. And then these are the trajectories they got. And you can see that basically they were doing the same thing. Qualitatively the same dynamics. You understand? So it's a completely different swimmer type, but ultimately it was doing qualitatively the same thing. This is back to the spheres and rods now. This is a two-sphere swimmer. This is something else that Yizar noticed, that it would engage in these periodic orbits. So look at this. It moves away from the wall, reorients, moves back to the wall. Look at it changing its orientation here. Changes its orientation, and then basically repeats in a non-linear periodic orbit. So it's not just traveling straight along the wall, it's kind of going up and down, like this, as it goes along, but it travels along the wall. And this was a nice face portrait. This is distance from the wall against the orientation. And you see this point there, in this center, that corresponds to the steadily translating orbit. Okay? So if you're a dynamical systems person, this is a stable center. It will just travel at constant speed. But if you start with different initial conditions, look at this one. That's one of these. Okay? Because basically you'll move away from the wall by changing your orientation, move back towards the wall, reorient, and keep going. Okay, so that's moving away from the wall, reorienting, which is here, and then move away from the wall again. And you'll carry on in a cycle. Okay. And here's a this is a three-sphere swimmer. 1, 2, 3. Did the same kind of non-linear periodic orbit. By the way, this is all published now. And this is what was cute, is that at Caltech, they were working with, Yizar was visiting from Israel, but he was working with, I think it was a student, and they actually, this is viscous fluid, a bath of viscous fluid, they actually did experiments. So this is a bath of viscous fluid. Look, you can see these cylinders here. These are sponges. You can imagine why they're there, to keep it afloat. So the thing floats on the top of the water, but these are motors, and they're turning these cylinders at different speeds. And so instead of the numerical experiments, they actually did actual experiments. And here's an actual video of an actual experiment. And it displayed these kind of nonlinear orbits that they saw. Everyone understand? Okay. So that was the evidence that was presented to me in 2010. And Yizar, who was at Caltech at the time, knocked on my door after his seminar. He saw me in the seminar, and somebody told him that I was interested in Stokes flows. And so a few days later, he knocked on my door and spoke to me. And he said, have you got any ideas about how to explain this? And I had some ideas, and I'm going to tell you about those next week. And I know Kiori knows about them, because she's written a paper that's a follow-up to something that I did just after this, with Yizar. There's some more slides here, but I'll leave those until next week when we talk about other things apart from micro-organisms. We'll just do 5 more minutes and then call it a day. Here's what we're going to do. We know we can describe Stokes flows with F and G. These are the two situations. Ideal flow is this, Stokes flow is this. Completely different physics, though. This is no viscosity. This is highly viscous. So completely different physics, but mathematically they're very similar. In particular, what happens if I take F to be 0? In the Stokes law. So if that's not there, psi, the stream function, looks exactly the same, except that I've got I use W here and G here. And you remember on Tuesday, I let W look like this, and you know what? Remember what I called this? I called this a point vortex. Remember? Well, what happens if I do this? And let's say F is 0. Very natural question, isn't it? The streamlines, of course, are exactly the same. Because this is a stream function. But while here, you should think of a hurricane swirling very quickly, air flowing a very high, basically envisaged fluid flow, going very quickly in a circle. This is like you put a pencil in honey, and you turn it, and it will drag the fluid around with it. If you're an ideal fluid dynamicist, you call this a point vortex. This is exactly the same thing kinematically, but guess what the low-Reynolds-number people call this? We'll see this next week in detail. This has a name, but it's not called a point vortex anymore because it's a completely different thing. Do you know what people call it? I'll show you. It's called a rotlet. And that's very interesting. Because mathematically, kinematically, they're the same thing. But because they pertain to different physics, we call it a point vortex in one context and a droplet in another context. But it's the same thing kinematically. Circular streamlines. Okay? So, here's something for you to think about before next Tuesday. What if I let f have a logarithmic singularity? Here, I took f0 and let g have the logarithmic singularity. But a very natural question to ask is, suppose I let f have a logarithmic. Okay. Have a think about that. After all, you know the connections between f and g and the physical variables now, so you can think about what it might imply for the physical variables. Okay, I'm tired and I suspect you are, so I think I'll finish today and we'll continue talking about point singularities, and then I'll show you how I model this system next week, next Tuesday.